It's foundational for problem. Okay. My bad. So, it's foundational for problem solving. So, it teaches logical thinking, pattern recognition, and structured problem solving. So, for example, um, like counting and probability help a lot when it comes to planning algorithm efficiency and like the outcome of an algorithm. It hinges a lot on math, even though it might not seem like it. It is very vital for a lot of what we do. Um, and then yeah, like say along the same lines of algorithms, the mathematical principles that we're going to look at guide how algorithms can become more efficient rather than just brute forcing everything, which wouldn't work. So concepts like modular arithmetic, they prevent overflow and like prime factorization, like we've talked about before here, that it supports encryption. Um, and then also for competitive programming specifically, basically every single problem that you're going to solve is going to have some sort of mathematical component. It might not be as obvious or overt as, you know, add two numbers or something like that, but it is absolutely rooted in math. So I'm going to talk about combinatorics. So first of all, what is combinatorics? It's the study of counting, arranging, and selecting objects in specific ways. I like to think of it as fancy counting because that's basically what it is. It helps in solving problems related to combinations, permutations, and probabilities. So does anybody know what like a permutation of something is?
Um, that's the like how many if you have like five objects, how many different ways you can like order them?
Mhm.
Or like if I want an order of three and I have five different objects, how many I can take three of those and order them?
Mhm. Okay, so like if I have the objects 1, 2, 3, 4, 5, um, how many ways are there to arrange five objects? Does anybody remember? Yep, 5 factorial. And everybody knows what factorial means? Cool, because I'll be talking about that. So, combinations. So, combinations are arrangements or like picking of objects where the order doesn't actually matter. So, in other words, like we have the n choose r formula here. In other words, that just means the number of ways to pick r objects from n objects. I'll explain that a little more clearly in the next slide. But the actual formula for calculating that I have up here. So it's n factorial over r factorial times n minus r factorial. Like I said, I'm going to talk about factorials because they're very important for this. So I'm going to go over an example. How many ways can a committee of 3 be formed from 5 people? So we can actually sit down and actually write this out to see how we can do that. So in this case, we have our n equals 5 and our r equals 3. So pretty simple. We just have to plug in the numbers. So we have 5 factorial over 3 factorial times 5 minus 3 factorial. And that's going to be equal to 5 times 4 times 3 factorial over 3 factorial times 5 minus 3 factorial. We can cancel out these two 3 factorials and just leave it with 5 times 4 over, and 5 minus 3 is 2, and 2 factorial is just 2 times 1, which is 2, and 5 times 4 is 20, divided by 2 is 10. So that means there's 10 ways that you can pick 3 people from a group of 5 to form this committee, right? And I have on the next slide just an example like if our people are Alice, Bob, Carrie, Derek, and Edward, then there are 10 ways, and I've listed the 10 here. And take notice of the fact that if in this group I have Carrie, Derek, and Edward, that is the same group as if I had like Derek, Carrie, and Edward, or Edward, Derek, and Carrie, like in a different order. It's the same group. It's the same group of 3 people. So, like I said here, the order doesn't matter for combinations. But for permutations, the order does matter. So the formula is a little more simple. We don't have to divide by r factorial. It's just n factorial over n minus r factorial. And that is, saying it in a different way, it's the number of ways to permute, that should be r objects from n objects. So as opposed to the slide before where a group of Carrie, Derek, and Edward is the same as a group of Edward, Derek, and Carrie, in permutations, they're actually different because in the permutations, the order matters. So I have another example up here and we can actually do this. So you have 4 books, but your shelf only has space for 2 of them. In how many different ways can you arrange 2 books from the collection of 4? And I have a little note here that order matters here because the bookshelf is going to look different depending on, the order in which I place the books. If I place a bigger book next to a smaller book, it's different than if I flip them around. So the way we can do that is we can look at our n is going to be equal to 4 and our r is going to be equal to 2 because I have a group of 4 objects and I'm picking 2 objects, and how many different ways are there to arrange those 2 objects from the 4? So just some more math here. 4 factorial over 4 minus 2 factorial. That's going to be equal to 4 times 3 times 2 times 1 over 2 times 1. And we can just cancel these out. And we're just left with 4 times 3, which is equal to 12. And that's exactly what I have on this next slide here. So say that my books are Harry Potter, The Hobbit, Great Gatsby, and Catcher in the Rye. I have all 12 ways to arrange 2 groups, or 2 books from that group, if you pick 2 of them and arrange them. So notice that on the board there, number 1 is Harry Potter and The Hobbit, and then number 4 is The Hobbit and Harry Potter. The order does matter here. Those are 2 distinct arrangements. So one more thing for combinatorics. This is a little more discrete mathy than combinatorics, but it is technically a combinatorics thing. It's called the inclusion-exclusion principle, and it's very simple. So it's a formula for counting the elements in the union of overlapping sets where you can correct for double counts. So if I have, in my example down here, in a group of 30 students, 18 of them like math, 12 of them like programming, and 6 of them like both math and programming. So how many students like either math or programming, not both of them? So in this group of 30, 18 of them like math. That doesn't necessarily mean that each of those 18 only likes math. So to calculate how many only like math and only like programming, we just have to add up the sizes of the groups and subtract how many there are in the overlapping group, which would just be 18 plus 12 minus 6 because 6 of them like both. So that leaves us with 24. That's a principle that we use a decent amount when we're talking about sets. It doesn't actually tell you which elements from the original set only like one or only like the other. It just tells you how many of them there are. So this can be helpful for some things. Yeah. Next, I'm gonna go over number theory. It sounds a lot cooler than it is. It's just talking about numbers. So it's the study of properties and relationships of integers. So if you ever heard of a prime number, that's something that they study in number theory. Can anybody tell me what a prime number is? John?
Number whose only factors are itself one.
That's correct. So, number theory is essential in programming because you have to understand patterns of integers, the divisibility of integers, prime numbers, and also modular arithmetic is super important, which I'll explain a little bit more. First, I'm going to explain prime numbers and divisibility. Like John just so helpfully told us, prime number is a number whose factors are only 1 and itself. I'm sure you've talked about this like algebra class before. So they're obviously prime numbers also have to be greater than 1 because 1's not prime. That's just one of the conditions. It has to be greater than 1 and it has no divisors other than 1 and themselves. So a number A, as far as divisibility goes, a number A is divisible by another number B if and only if there exists an integer x such that B times x equals A. That's a little mathy, but I can break that down a little bit. So I have an example down here. If A is 10, then B can either be 1, 2, 5, or 10 because there exists an integer. There exists an integer that I can multiply by B to get my A. So 2, I can multiply by 5 to get 10, and obviously vice versa. So that's just the definition of what divisible means. It just means that it evenly goes into it. If I divide A by B, there's not going to be any remainder. That's the definition of divisibility. That's also pretty important in programming. So, and then I have a outline down here. B can't be 3, 4, 6, 7, 8, or 9 because if I try to divide 10 by 3, there's going to be a remainder 1. If you try to divide 10 by 4, it's going to be a remainder 2. So yeah, that's one of the big parts of number theory is divisibility in prime numbers. And the other big part is modular arithmetic. So we've touched on this before, I believe, in one of the CTF meetings they talked about it. But basically, modular arithmetic deals with remainders of numbers. So for example, you have taking a number A and modding it, quote unquote modding it, by another number B, leaves us with the remainder of dividing A by B. So if my A is 17 and my B is 5, 17 mod 5 is going to be equal to 2 because if you try to divide 17 by 5, you are left with a remainder of 2. So I have a quick example of how modular arithmetic can actually be super helpful for stuff. If I'm on hour 21 of like a given day, right? Hour 21 is going to be 9 p.m. What time will it be in 13 hours? That's pretty easy to do, like in your head. You can just be like, oh, okay, it's going to be 3 hours to midnight and then another 10, so it's going to be 10 a.m. But if the question was, if I'm on hour 21 of a day, what time will it be in 152 hours? That's not as easy to do in your head, but I have an example here. Basically, you can just add 21 and 13 together and mod that by 24 because that's how many hours there are in a day to find the remainder. So 21 plus 13 is 34, and 34 is equal to 10 mod 24 because you divide 34 by 24 and you're left with a remainder of 10. So that means it'll be 10 o'clock, 13 hours from 9 p.m. Again, that sounds pretty obvious, but if you're dealing with bigger numbers than that, not super obvious. So this modular arithmetic is actually very helpful. One of the final aspects of number theory that's incredibly important involves prime factorization. So has anybody heard of the fundamental theorem of arithmetic? I mean, I have it up here, but has anybody heard of that? Yeah.
Yeah, you
Okay.
mentioned it 30 seconds ago.
But yeah, so the fundamental theorem of arithmetic is every positive integer greater than 1 can be uniquely represented as a product of one or more prime numbers. So basically, if given any number greater than 1, I can represent it by multiplying prime numbers together, which will equal my number. And uniquely is the important thing here because I can't get two different prime factorizations of the same number. 60 is only going to be equal to, 2 times 2 times 3 times 5. I can't get another prime factorization of 60 because that's not possible. That's what the fundamental theorem of arithmetic tells us. And the fundamental theorem of arithmetic is very helpful when it comes to encoding or dealing with, say, the largest or the least common multiple, which I will talk about soon. It's very helpful for that kind of stuff. So applications in programming, like I just mentioned, the least common multiple is used often. And does anybody know what the least common multiple and greatest common divisor of two numbers is? Let's hear it, John.
So the names are a little counterintuitive, but the greatest common divisor is smaller than both the other, smaller than equal to that divided in both. So if we had like 4 and 6, it would be 2 because 2 is the largest number that divides cleanly into 6 and cleanly into 4.
Yep.
Whereas the least common multiple is kind of like it's like the smallest number that both of them divide. So it's always going to be greater than or equal to
Yep.
the largest one, basically.
Yeah.
And basically, you can use the GCD to calculate LCM, I think.
Yeah. Yeah, John is exactly right. So yeah, the greatest common divisor, like John said, is the largest number that's a factor of both A and B. So the greatest common divisor of A and B, and factors, we all know what those are. It's just a number that evenly divides the number. It evenly divides a given number. I talked about that earlier. Least common multiple, used less often, but also fairly often to basically the least common multiple is the lowest number such that both A and B divide that number. And like John said, it can technically be A or B could be the least common multiple of A and B, depending on how the numbers are set up. I have some examples in the next slide, but both of these are used fairly often in both competitive and non-competitive settings when we're talking about programming. The GCD is used a lot more often than the least common multiple is, and specifically the GCD is used where you have to simplify ratios. So if I want a simplified fraction, you have to make sure that the GCD of the numerator and the denominator is 1, meaning that it's as simplified as it could be. And then least common multiple is used less often, but it is still a fairly common algorithm. It's used more specifically when you need to like align things. That's kind of a weird way of putting it without having an actual example. But if I have something that's like rotating and I need something to align properly, I can find, you know, a multiple of this thing and see when it lines up with another. That's kind of a convoluted example
Like
or
2 gears,
description.
maybe? 2 gears. To
Yeah.
make sure it's not unevenly distributed.
Yeah, something like that. Yeah. So I have some examples up right here. So given A equals 48 and B equals 12, finding the GCD is pretty easy. There's an actual formula for it, but you don't really need to know the formula. You just need to be able to understand what it is because the computer will do the rest for you. So the GCD is the largest number that divides both. Okay, I forgot to put the number, but I've been editing these slides, but it should be the divides both 48 and 12. So the divisors of 48 are 1, 2, 3, 4, 6, 12, 16, 24, and 48. And the divisors of 12 are 1, 2, 3, 4, 6, and 12. And the greatest number that both of these sets have in common is 12. So that means our GCD of 48 and 12 is 12. And like we explained earlier, it can be A or B depending on how it's set up. And this one happens to be set up to be have B as the correct answer. So given A is 26 and B is 16, what is the least common multiple? This one's a little more annoying, but not too annoying. So you just have to find all the multiples of 26. So 26, 52, 78, blah, blah, blah. Keep adding 26. And the multiples of 16 are, 0, 16, 32, 48, 64. Just adding 16 every time. And as it turns out, their least common multiple, which is the lowest number that both of these sets have in common, is 208. So, another quick note here is that the least common multiple is associative. So if I wanted to find the least common multiple of 26, 16, and another number x, I can just find the least common multiple of 26 and 16, like we showed here is 208. And then I can find the least common multiple of 208 and x, and that will give the correct answer for the entire question, right? Because it's associative, you can just apply it to both of them separately, and it will work. So that's all that I'm going to go over for math, but I'm going to actually do some problems and explain how we use the math and the actual mathematical foundation of the problems. So first one we're going to go over is from CSES, which is a problem set I've talked about before, but just have to pull this up. So let's go to this problem. It's going to load. All right. This one is called coin piles. So you have 2 coin piles containing A and B coins. Nope, not working. Fantastic. Thank you. I'm just going to duplicate my screen. Is the stream still working? That might have broken the stream. Let me just fix the stream. All right. That should be working. So, just to describe the problem, you have 2 coin piles containing A and B coins. Zoom that in a little bit. On each move, you can either remove 1 coin from the left pile and 2 coins from the right pile, or you can remove 2 coins from the left pile and 1 coin from the right pile. So you can do 2 from one and 1 from the other. And the task is to find out if you can empty both the piles. So given the starting number in pile A and the starting number in pile B, is there a way to actually empty both piles? And just thinking about it, you know that it's not always true, because there's a possibility that like in this example that they have here, if both piles start with 2, like I have 2 in this pile and 2 in this pile, and then my first move, say I'll subtract 2 from the left one and 1 from the right one, that'll turn this into 0 and this into 1, and one of them is left with 1, meaning that it's not possible to evenly remove from all of the coins from both piles, right? So does everybody get the actual problem statement here? Does that make sense? So, does anybody have any ideas of what we can do to efficiently check it? Because we don't, keep in mind here that these numbers can be, they give us bounds here, they can be as big as 10 to the 9, which is, what, a billion or something like that? That is way too big to just try to simulate, you know, choose random ones here. Take 2 from this one, 1 from this one, 2 from this one, 1 from this one. That's way too big to try to simulate the actual process. So we're gonna have to use math to figure out the process, or to just figure out an easier way of telling it. So can anybody think of any ideas that could be that we talked about that could be helpful for this? Let's hear it, John. It's a good thought. You have an idea? Yeah.
Could you explain?
Yeah, so so for each test case, we're being given the starting size of one pile of coins and the starting size of another pile of coins. And we need to figure out if it's possible using this process that they've described, where you can take 2 coins from one and 1 coin from the other, or vice versa. Take 2 coins from this one and 1 coin from this one. Is it possible to empty both of them so neither of them have any left? And basically, you know, if one only has 2 left and the other only has 1 left, you can do that, right? Because you can just take 2 from this one, 1 from this one. But if there's 1 left in here and none left in here, I can't take 2 from either of them. So that means it's not possible to do that. So, any other ideas on maybe just an immediately obvious thing that is just like, there's no way this one works? Let's hear it.
Like one can't be less than double the other. So if you have
Yes, yeah.
if you have 101 and only 5 in the other, then that can't work, because after 5 draws, the logic takes 1 and has to.
Exactly correct. So that is one of the precursors. The I'll say it like this. So the size of the larger pile cannot be greater than 2 times the size of the smaller pile. So basically what that means is if I start with 5 in the left pile and 2 in the right pile, we know this is not possible, because there's no way I could take 2 from this one, make that 3, and only 1 from this one and make that 1. There's no way that basically subtracting 2 from the bigger one every time and only 1 from the smaller one, there's no way it could like catch up, I guess. There's no way to make it so they're equal, or even close enough to be equal, right? So that's, John correctly identified one of the 2 precursors to make this problem possible to like take out the piles, right? Can anybody think of the other one? This one's a little harder to identify, but think about how many coins you're taking out every turn, if that helps.
You can't have both piles have the same number of points, right?
Yeah, that one works too.
So you can't have an even number of piles?
Well, not necessarily, actually.
If both piles are the same height and they have a number of coins that's a multiple of 3, you're guaranteed to have a solution.
Yeah. So another way of phrasing that is if the adding them together is not a multiple of 3, there is absolutely no way to have a solution because you're removing 3 coins every time, like a total of 3, 2 from this one from this one. So if the two piles don't add together to be a multiple of 3, then I know there's no way I can do it. Right? So the second one is what we've just identified. So, and as it turns out, these are the only 2 things we need to check to determine whether or not you can remove them, right? Because these are basically the only edge cases where you know that there's no solutions. Other than that, there is definitely a solution. Right? So, the next part comes with actually programming it and solving it. So, what I'm going to do is pull up a VS Code. And this one is called CoinPiles, so that's what I'm going to call the file, coinpiles.py. So, next we got to look at the input. Like we talked about last time, you want to make sure you're reading in the input properly. So, looks like they give you an integer t as the first line, and after this there are t lines, so, you know, the number of lines after that is equal to t, and each of these t lines has 2 integers which represent the number of coins in each pile. So let's read in t, and that's just a quick int of input, and we've read in the first line. Let me actually turn this off. Disable completion. So next we want to read in the t number of lines. So for I in range t, that's going to loop t times as we've learned before. And I'm going to split the input into A and B like this. So just to show you what it looks like, I'm just going to print A and B for each one. And I'll copy and paste this input in just to show you what our current setup looks like. So for each one, it's taken in A and B by splitting each line, and then it prints out A and B. So just to confirm that we know what we're looking at. Next, what we want to do is check these conditions that we've outlined. So the first condition is the size of the larger pile cannot be greater than 2 times the size of the smaller. That's a very verbose way of saying that the minimum of the 2 piles has to be less than 2 times the size of the maximum of both piles. So I'm going to do that. I'll call it maximum is equal to the max of A and B, and minimum is equal to the minimum of A and B. And what that does, it just takes in 2 arguments and finds which one is greater, and this one finds which one is smaller. Does that make sense? Next, what we're going to do is do a conditional that checks if 2 times minimum is greater than or equal to greater than or equal to the maximum, meaning that the maximum is small enough to be achievable. It doesn't break the rule. That's one of the conditions. Then I'll do another if statement that says A plus B, like we've identified here, the sum of the 2 piles has to be divisible by 3. So we're taking the sum of the 2 piles, A plus B, and using the percent sign, which is the character that or the operator that represents modular division. So what this is going to return is the remainder of dividing A plus B by 3. So if a plus b divided by 3 is equal to 0, meaning that it is evenly divisible by 3, in this case, we can, I'll keep a list of results. We can append to the results list, and it looks like they want capital YES. And then we can just conclude it with an else statement with results.append no. Because if it doesn't meet both of these conditions, then it certainly is not possible. So I'll log in here and we can submit it and see if it's right. So submit. I'll choose the file from my desktop. Actually, first what we want to do is just make sure that it works with the test case that they've given us, because if it doesn't, then it definitely won't work. But I have identified a problem. I don't actually print the results. That is an issue. So it looks like they want it line separated. We can just print looping through all the results, just printing the result on each of their own line. Good thing we tested it, because that would have been wrong. Yes, yes, okay. Looks like this needs to be in here. Because what was wrong the first time is this condition was met, but this condition wasn't, so it never actually got to this else statement. Just a quick fix for that, and then it should work. Let's test it out. And it looks like we got the same answer that they got for the test case, which is yes, no, yes. And that's what we got, so let's submit it. Accepted, yay. So that means we got all of the test cases right, and it looks like they have 3 test cases. Fantastic. So, as you can see, with this invisible test case that we weren't able to see before submitting it, these piles are like way too big for us to try to simulate them. So we had to come up with a solution that uses the math principles that we talked about. Does that make sense to everybody? Are there any questions about this question? No? Looks like I explained it really well then. All right, next one. This one's from Project Euler, which is a little different than the CSES problem set. Because for Project Euler, you don't actually submit code. You just write code to find the answer and then submit the answer. So it's a little different of a setup. It's not really competitive as much as CSES is. This one's more of just, can you do it? And as it turns out, this is a problem that we can do. So let's go over it. So smallest multiple. 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. So that means that 2520 divided by 1, or mod 1 is 0, mod 2 is 0, mod 3 is 0, mod 4 is 0, all the way up to 10. And then our task is to find what the smallest positive number that is, what is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20. So one nice thing about Project Euler is that there's not a time limit, because you don't actually submit code, you just submit the answer. So if you wanted to write the worst brute force solution ever and wait 3 months for it to complete, you could do that and then submit the answer. I don't want to do that, so we'll talk about a solution that gives it to us in a reasonable amount of time. So, first thing we want to observe is what I talked about earlier. The least common multiple is actually associative. So if I want to find the least common multiple of multiple numbers, I can just find the least common multiple of these two, and then take that least common multiple and use that to find the least common multiple of the next number. It makes a little more sense if I write it down, so I will write it down. So, given, say, 4 numbers, I'll do 2, 3, 4, 5. If I want to find the least common multiple of these, I can just find the LCM of 2 and 3, which happens to be 6. Then, using this 6, I can find the LCM of 3 and 6, which happens to also be 6, like we talked about. But I can do 4 and 6, and that will give us, looks like 12. Then, using this 12, find the LCM of 5 and 12. And then that gives us 60, I believe. Yes. So, the least common multiple of 2, 3, 4, and 5 is 60. And like I explained, the least common multiple operation is associative. So I can just take the operation from the last one and plug it into the next one, and I will get the answer without having to keep track of all of them and then, slowly make it go down. So that's really the big thing that we have to understand about this problem, is that the least common multiple operation is associative. And then we've kind of solved the biggest part of this. So call this one, what is it called? Smallest multiple. So what we're going to do for this is find or initialize a multiple variable to start at 1. Just because I know that I have to have this defined to be something, and so it's just easy to do 1, because 1, the least common multiple of 1 in any number is whatever number you give it. So then I'm going to loop through all the numbers, and it looks like we need to go to 20. So remember, the range is exclusive, meaning that it doesn't include the last one. So I'm just going to go from 1 to 21 to include all the way up to 20. And we're just going to recalculate the multiple to be equal to, one thing I forgot is, the math module in Python provides an LCM function, which stands for least common multiple. We can just do LCM of multiple and our current I. And then from there, we can just print multiple. So what this is doing is, go back to my whiteboard, given our list from 1 to 20, it's going to take the LCM of this one and this one, which is 2, and then it's going to take the LCM of 2 and 3, might be easier to do this. So actually what it's doing is taking the LCM here, and then it's also taking here and here, which is also 2. It's kind of repeating some extra stuff because it should be skipping one every time, but it doesn't really matter. And then from this 2, which is the result of our last operation, we're going to take the LCM of 2 and 3. And then we're going to take the LCM of 2 and 3 and 4. So basically, does everybody get that process? We're calculating the LCM for each one from the last LCM until we get all the way up to 20, which, because the least common multiple operation is associative, we can just continue like doing that until we get to 20, which will give us the answer. So, assuming I haven't made any errors in my code, this should work. And it looks like the number is 232,792,560. So let's actually submit that to Project Euler and see if we're right. I have to sign in, I guess. as you can see, I've already solved this one, and the answer was indeed 232 million, blah, blah, blah. So, does everybody understand how that works? Like why we were able to just do this simple process to be able to calculate it? Any questions about that? No? Cool. And like I said, the cool thing about Project Euler is this is a very efficient solution, but say, for example, this needed to be like 2000. This will probably still be pretty quick, but yeah, it's pretty quick. But if the number was a lot bigger, Project Euler doesn't depend on your code being actually good. You just have to submit the answer. So if it was asking you to find the least common multiple of all the numbers from 1 to 1999, that would be the answer. Maybe they're going to do that one day, but I doubt it. So another question that we can go over is also from Project Euler, and this one is problem 1. Now, as you can see, I've already solved it, but let's go about how we would actually solve it. So this one is, if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. And the sum of these multiples is 23, because 9 plus 6 plus 5 plus 3 is 23. So our task is to find the sum of all the multiples of 3 or 5 below 1,000. This one is very easy. I'm sure most of you can imagine a solution in your head fairly quickly. And it's exactly what you think. So first what we're going to want to do is initialize the sum to be 0. Then we're going to make sure, yeah, all the numbers below 1,000, meaning that 1,000 is not included, so I can loop all the way up to 1,000. Then if I mod 3 is equal to 0, or, just like it said here, multiples of 3 or 5, not and, so I'm using or I mod 5 is equal to 0, meaning this line means it's checking if I is divisible by 3 or 5. If it is, I'm going to add I to the current sum. Then at the end, I'm just going to print the sum. That one's a fairly simple one, and it looks like the answer is 233,168, and that is indeed what the code got. So that one's really simple compared to the ones we just talked about, but it does kind of drill into you how you used modular arithmetic. So if I, percent modulo 3 is equal to 0, that means if I is divisible by 3. If I do something like print 20 modulo 3, it's 2, because 20 mod 3 is equal to 2, meaning that there's a remainder of 2 when you divide 20 by 3. So that's how the modulo operator works. Does that solution make sense to everybody? That one's fairly simple. I do have one more to go over. This one is on Caddis. Caddis, unlike Project Euler, actually requires you to submit code, and it has a time limit, 1 second, meaning that you can't just write a brute force solution. So we'll have to actually approach this one with a little bit more thought. So, given two integers a and b, a modulo b is the remainder when dividing a by b, like we talked about. This one's just explaining what modulo is. So the task is to write a program that accepts 10 numbers as input and outputs the number of distinct numbers in the input if the numbers are considered modulo 42. So that's a gross way of saying, given a list of 10 numbers, if you divide them by 32 and find their remainders, how many distinct values are there? So if my numbers are 42, 1, 2, 3, 42 mod 42 is 0. 1 mod 42 is 1, 2 mod 42 is 2, 3 mod 42 is 3. These are all distinct. None of these are the same. They're all unique values. So this list of numbers does work, but if, for example, the numbers were 43, 1, 2, 3, 43 mod 42 is 1. 1 mod 42 is 1 also. 2 mod 42 is 2. 3 mod 43 is 3. These numbers are not unique because 1 occurs twice. So we're trying to find how many unique numbers there are given a list of numbers mod 42. So in this example, it's just the numbers 1 through 10, and none of these are going to be the same mod 42 because they're all just going to be, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means there are 10 distinct values in there. This test case is just all multiples of 42, meaning that all of them are going to have the same value, which is 0. They're all going to be 0 mod 42, which is why there's only one distinct number that is being output, 1. This one, there are 6 distinct numbers because, 39 mod 42 is 39, and so is, actually that one's unique, but 40 mod 42 is 40, 82 mod 42 is also 40. So those ones are going to map to the same values. So the output that is looking for is how many distinct values there are. And the nice thing about the input is that there's only 10 non-negative integers. So we can just hard code that value to read in 10 values. They don't have to read in a bunch of them. So yeah, let's do this one. So, does anybody have an initial idea of like what we should do? Go back to the problem statement. So what's the first step in any Caddis problem?
Take input.
Yes, that is correct. Thank you, Burke. Take in input. And the input comes in the form of 10 lines with one integer each on them. So what we can do is just for blank in range 10. This loop is just going to run 10 times. I used blank because I don't actually care what this variable is. I'm not going to be using it. I'm just going to read in 10 numbers. And I'll actually just initialize an empty list called nums where I'm going to store the numbers. Current num is going to be equal to the int of input. So I'm taking input from that line and converting it to an integer. And then I'm going to append that to my nums list. So what that looks like, if I take the test example here of 1 through 10, it's just a list with all these numbers in them, right? Fairly simple. Now what we got to do is determine an easy way to do this. Does anybody have an idea of how we can find how many of them are unique, mod 42? Bueller? Nobody gets that reference. Fantastic. What I thought of doing was, instead of adding the number, I'm just going to add the number mod 42. So my list with 1 to 10, the list is going to look the exact same because 1 mod 42 is 1, 2 mod 42 is 2, and so on and so forth. But if I take this one, this test case, and run the script again, they're all zeros because all of these are equal to 0 mod 42. So now the only thing we have to do is, given our current nums list, find how many of them are unique values in there. And Python has a really easy way of doing this. There is a set data type in Python, and if I look at a set, a set is an unordered collection of unique elements, meaning that if I convert a list to a set, it's only going to contain the unique elements. So I'm going to put set of nums for this one. And that set is just going to have one element in it, which is 0, because that was the only unique element from here. What it does to convert a list to a set is it starts with the first one, puts it in there if it's not already in the set, and then goes to the second one, puts it in there if it's not already in the set, and so on and so forth. This one only put in the first one because the all the rest of them are the exact same because it's already in there. Now what we have to do is print the length of this set, which, as we've already shown, the set contains all of the unique elements. So finding the length of how many unique elements there are gives us how many unique elements there are in this set, or in this list that we're being given. So if I take that and put it in the list, it gets 1. That's a correct answer. Then we'll use this test case here, run it again, input it, and we get 6, also the correct answer. And just to make sure, we'll put this in and do the exact same thing and make sure it doesn't get it wrong. And we get 10. So next, all we got to do is actually submit that code. So I will copy the code, start coding, put it in there. Cool, accepted. That means we got them all right. So does that make sense to everybody? What the solution I just went through there and how that works? Again, this one's not quite as complicated as, say, the coin piles one. I wanted to get that one out of the way first. That coin piles one is easily the most complicated of the ones I've talked about. But does anybody have any questions on this? No? Fantastic. That means I explained it really good. So that's all I have for you today. Are there any other questions, not specifically about that problem we just solved, but just about combinatorics or number theory in general? Because I'm willing to answer those too. No? Cool, man, I'm really good at explaining shit. All right, that's it then.